Good morning, everybody. This is Ross Holleron from KNAUF Insulation, and I'll be co-presenting with Jelle Langmans from KU Leuven University. Jelle is controlling the slides for me to start with, and it will become apparent why as we go, because Jelle will be sharing a lot of his research. So, Jelle, if you could just click on for me, that would be great, please. So a little bit of an overview of the aim for this webinar that we have produced for you. I will give you some background to the issues, why warm roof construction, why an Insulation Manufacturers Association would be involved in such research. Jelle will tell you more about the influences on real performance from his own studies and work, and then we'll look at some best practice guidance, and most importantly, from our perspective as manufacturers, how do we then use that knowledge and research in a way that can be disseminated across the industry. So if we could move on to the next one, please. By way of a soft introduction, many of you, all of you, I'm sure, are aware of the increasing requirements for better thermal performance from the fabric of the building, also the services and the low and zero carbon generation systems. And what we have seen as manufacturers, and you as industry players as well, I'm sure, is that as we've pushed for these higher levels of performance, awareness and an acceptance that there can be a difference between what you design the performance to be and what's actually achieved, even without the vagaries of a human being living in the property or using it as an office, can be quite significant. And much work has begun across Europe, Belgium, France, Germany, and the UK as well, in understanding those key influences that make a difference between what we design and intend to deliver and what actually gets handed over to the people that own or live or use the building. So I wanted to share just one example of that type of work. It's a UK example. So post-Brexit, you may feel it's not relevant, but actually the realities of a construction site and of a design team and of local planning requirements are often very similar. So Jelle, if we could just move on one, please. Okay, so what did we do in the Zero Carbon Hub project? We managed to get the government, the Department of Energy and Climate Change, as it was known at the time, and communities and local government who control building standards to part fund an industry research project. So representatives from 60 different companies and groups came together, and as you can see from the map, our aim and objective was from original concept design and planning, and in this case it was new build residential. We looked to map the key influences on the difference between the design performance and what was actually built and delivered in the building itself. So we started at concept design and planning. We looked at detailed design, procurement, construction and commissioning, and also the verification and the testing requirements that are weaved in and out and around the delivery of the products in their design and their lab testing, through to what a building control person may do to deem the property acceptable for the standards. We started off with around 120 issues, almost like a shotgun spread across a wall of potential issues, and then by reviewing sites themselves, looking at academic research, talking to the industry, we managed to filter that down to 15 issues, which are the ones that you can see here, which were deemed priorities for action. And by that we meant there was clear emerging evidence that when these things occur, they also have the potential to have a high impact on the as-built performance. And they fell into three categories, which were knowledge and skills, responsibility and communication. So the ones that I've highlighted feed nicely into this next step. So there was inadequate understanding of the design team as to how to actually create good energy performance. There was very little, if any, consideration of the skills of the people who would actually construct the building during procurement. Those teams on site often lacked knowledge and skills, and also there was very little attention for quality control of energy-related issues on site. So if you could just move on for me, please, Jelle. So within that context, and at the same time, a specific piece of research came out from the British Board of Agreement in the UK in 2012, where they used a modified hot box so they could reflect the angle of pitched roof insulation, and they could change the airflow to reflect different wind speeds through that construction, because there were concerns emerging within the industry about the way that rafter level, pitch level insulation was performing. What they discovered, as you can see from the nice simple chart, is that as the wind speed increased, so their maximum speed they used was 7.5 meters per second, which is leaves moving on a tree, branches gently swaying, not a gale or a hurricane. They discovered that actually you could get a 90% increase in the U value that was measured, so 90% worse, more heat loss through that structure. The most interesting thing for us as an industry was that actually the construction type and the way the roof types had been built, because it used a variety of insulation materials, was counter to what those more informed designers, product manufacturers, and the research community were already aware of. So it posed the question to us in Eurima, why doesn't the industry know that this is the wrong way to build? And from our perspective, how can we help them understand how to use our products better? And that's where Jelle's study came in. So if we move on now, I will hand you over to Jelle, and he will tell you more about how they reviewed existing research and developed some best practice guidance.
Okay. Hello, everyone. My name is Jelle Langmans. I'm speaking from the Building Physics Research Group from the KU Leuven. And we made this project together with Eurima. And the aim of our part in this story is to collect all the research which was already done on airflows on the impact of airflows on the thermal quality of pitched roofs. So to be honest, we didn't do any new research for this project. The only thing we did is collecting everything which was out there from the 60s onwards, because a lot of things have been done on this topic. And what we did was collecting all the information, all the research, and we made a nice review paper on this, where the existing knowledge is collected. And what I will do in this presentation is go through the main findings, or the main airflow patterns which influence the energy performance of pitched roofs. So actually we can distinguish three different kind of airflow paths. The first one is forced exfiltration. So as a result of an air pressure difference from the inside to the outside, we have an airflow from the warm conditioned air to the outside, which is probably the most known. The second one is internal air rotation, driven by thermal differences between the inside and the outside. Air starts to rotate inside, or might start rotating inside the insulation or around the insulation, reducing its energy performance. And the third one is wind washing, driven by wind pressures. Airflow can flow through the insulation without entering the building, but the cold air introduced in the insulation also reduces the energy performance of the insulation layer. So these three airflow patterns have been studied over the last 30-40 years, and what we did is collecting all the research findings in this paper. This is often, like the thermal performance is often expressed by the Nusselt number, which is the ratio between the thermal resistance with pure conductivity, so without air convection, over the thermal resistance in which thermal conductivity and airflow is encaptured. So this unit is used in this presentation to express the effectiveness of the insulation. So first, exfiltration. This is probably the most known, and today there's a lot of emphasis on improving the air barrier, which can reduce the forced exfiltration. So I will briefly go through this slide because it's the most known airflow pattern, and also the one which is, I think, as well known. So you can measure the performance of the air barrier with the blower door test. So this airflow pattern can be easily reduced by doing an air pressurization test and finding the leaks and putting forward the air barrier system thresholds as I'm listing here and as they are investigated in academic world. So these numbers can be maintained. The second, which is often overlooked, is air rotation. So also without having a connection between the inside and the outside, air can have an impact on the thermal performance of insulation materials. And within the world, or within the airflow pattern of air rotations, we can distinguish three different patterns. The first is like when we have very low density insulation materials, air might loop inside the insulation itself. The second pattern is when there are leakages around the insulation layer, air can loop around the insulation layer in these air paths. And the third one is when the cavity is not completely filled, we can have patterns at the airspace which is left in the cavity. To illustrate what the impact can be of even small leakages, this graph shows the yearly heat loss increase of as a result of air leakage or air paths. So from the left to the right, there are 6 different configurations. On top of the graph, you can see the red line, which is expressing the position of a leakage, and the size of this leakage is ranging from 1 millimeter to 5 millimeters. And the bars on this graph express the increase or express the yearly heat loss. So you can see that going from left to right, the increase of the heat loss can, for example, for a leakage or an air path of 3 millimeters and having a path left and right of the insulation layer, can have a 10% increase of the energy performance, reduction of the energy performance. In this graph, I have to mention that the red dots express the situation where there is an air barrier on both sides of the layer, and the bars express the situation where there is also an imperfect air barrier at the inside. So if you have a combination of the first one, an imperfect air barrier in combination with small air leakage at one side of the insulation, the impact of the air rotations is even much worse, as you can see here. So this slide shows that even very small leakages of 3 to 5 millimeters can have a large impact on the energy performance or the performance of the insulation layer in pitched roofs. If you see like advertisements, everything is perfectly done, but I know from my own experience that in renovation projects, it's often very difficult to have a perfect installation of the insulation layer. So when there are many details, it's often better to go for loose fill insulation. When there are very straight cavities, it can be filled with bed insulation. To have an overview of the requirements which are put forward in the research, I have this table, and main findings are that you have to be below a certain density, because very low density insulation materials or very high air open materials have the highest risk for the introduction of natural convection. And the second requirement is filled insulation compartments and avoiding small channels around the insulation layer. This brings me to the third airflow pattern, which is wind washing, also often overlooked. Like as I told in the beginning of this presentation, most of the emphasis is today on the air barrier system at the inside, but also the air tightness of the outer layer. So the underlay is very important to improve the performance of the insulation layer. And what today is often overlooked is the connection between wall and the underlay elements, as you can see on this slide. So there should be a connection between the wind barrier at the roof and the wind barrier at the wall elements. We did some investigation on this in laboratory conditions, and we found that these 3 connections had very good results. So in these details, you can see that there is a connection realized between the outer underlay and the inside air barrier. For example, at the roof wall element, you can see that the blue underlay is connected through a red weighting foil to the inside air and vapor barrier to improve the wind tightness and to not allow that cold wind can enter the insulation layer at that point. So from these investigations, we found that it's much more important to seal the edges of a roof rather than sealing all the joint overlaps between the underlay. And these are table values from the literature where threshold numbers for the air permeability of underlay materials or wind barriers are listed. It can be checked, so there can be a quality control, but then you have to do a second air barrier test, a second blower door test. You have to do one at wind tight stage and then a second one at airtight stage. I think Norway is at this point the only country which has experience in this. They are pushing more and more to have these 2 tests to have a quality check of the outdoor air tightness. And then this is my last slide, just to have an overview of which kind of requirements that are listed in the literature. So we have requirements on the air barrier level to avoid forced exfiltration. We have requirements on the insulation layer to avoid natural convection, and we have requirements on the airtightness of the wind barrier to avoid wind washing. So this was my presentation. I give the word back to Ross.
Thank you, Jelle. That's brilliant. If we could just move on to the next slide, please. So the question here, of course, is Eurima helped to put the work together, but how do we actually use it? Because the challenge that we saw at the beginning was that, and as Jelle's described for us, much of the knowledge was out there in the academic world and maybe in parts of the design world, but not in the mainstream industry. So one example from KNAUF, but the other major manufacturers that are involved in Eurima are also doing this type of work in the field. We've been working with a social housing provider in Belgium, looking at their houses, in this case they're sort of 1970s houses, and part of the work that we did looked to take the work from Leuven and the previous experience and turn it into something we could actually trial on site. So we worked closely with the installers. You can see on the bottom left that this is a part way through the installation. So we're in the roof space, and the beige color is the outer wind washing membrane. It's a weather membrane. This is a retrofit project. So beyond that, we have the rafters, and then also the sarking board, the weather protection board, and then the tiles. So what we discovered by working with the installers is that as they arrived, their natural instinct was to install from the outside in, as one would initially think. So they put the weather membrane in, they put the insulation in, they held it in place, they put the vapor barrier on. And what we discovered at the bottom junction was that it gives you a very difficult detail, as we know from the work that Jelle described. So by planning the sequence differently and pre-installing what would ultimately be the vapor barrier at the bottom of the junction before they put the insulation in, we gave them a much easier sequence and more robust detail. We also then looked at what I call explaining to the point. So that's showing people what the different elements of the package of products that they're using actually do. So it may seem second nature and very obvious to the people on the webinar that the insulation is designed to stop the flow of the heat. But for example, if you're with a team that have never really had that explained to them, which elements, as Jelle's work described, the air movement in and around, the compression of the insulation at the corners, if you don't explain that to the team, then they think they've done a good job, but actually you can walk around and you might be able to put your fingers in between the insulation materials, or they won't quite have filled all the gaps because they think 90%, 95% fill is enough. And we obviously know that we want as close to 100% as possible. And the final part then is the QA. As Jelle highlighted, there are many things that you really can't test once the work is done, or you would have the introduction of a clerk of works, as it would have originally been called 20 or 30 years ago. And I'm not sure the industry has the financial capacity or the building control people have the desire to see that on every site. So our experiment, our thought process at the moment is, if you equip the people on site with the knowledge to understand where failures occur and what that might mean for their company later on, if it's found that the work isn't correct, or if damage happens to the building fabric by poor installation, they're more likely to do it well the first time. And one of the key parts of that is making good visual, the final picture on the right-hand side. So what do I mean by that? Well, we can all see that there's a vapor barrier in place. We can see that the tape is in place attaching it to the masonry, but because the vapor barrier has a degree of transparency and the silicone style sealant you can just see a stripe of behind is a blue color, maybe more by good luck, but it's very useful. You can actually see, if you walk into that roof space, that they have not only taped and overlapped the junctions and that the overlap is the correct 100 millimeters, but I can also see that the sealant is in place. So by designing the package of products that we provide to the installers in a way that they can actually see good, we really help them. Now, clearly, everything isn't completely finished. It's an ongoing process. It's a part of a cultural change, and that's why Eurima are supporting QUALICHeCK as well. If you could just click to my final slide, please, Jelle. So just as a summary, Jelle has described that actually we require a system approach, an outer anti-wind washing membrane. We need the right type of material in the middle. The critical part there is its ability to resist that internal air flow, so it's related to specific air permeability. Density plays a role in that, but obviously the density is different between the types of mineral wool, so it's important to actually look at the air permeability limit, make sure that the products are installed correctly so there aren't those air gaps, and that the air barrier system inside is nice and tight. But the key thing for us is that as we work this into our guidance for installers and for educating our technical sales teams as well, that we actually have something that's taken a step beyond the base academic research and collated it into something we can actually share with installers in toolbox talks and activities on site. So if we could click to the final slide, please. That is Jelle and my presentation, and we look forward to some questions and answers when the time is right. Thank you.